Why do I have a... Let's read it. Haha. I feel like we should make the color... Yeah, okay. So let's quickly do this. Black to move. What should I do? There. There. Black to move. Pawn's covering this, which is pretty nice. How about... If I go here, you'll probably go here. And then when you go there, I guess I can go here. Nice. White to move. What shall I do? If I go here, you take. I go here, king takes. This pawn is gonna take it if I don't. I could do that. And then I guess pawn takes. I don't know, mate. What? Because then pawn takes, and then I can put the bishop there. Whatever, I guess I was right. Anyways. What else do we have? Daily puzzle. Black to move. Pawn's covering this. Oops, I feel like it's this. And then you go here. What would I do from there? Can't really do much. If you go there, then I will bring my rook. I'm actually not too sure, mate. I feel like that makes more sense. Oh frick, I can't even move that, I'm trolling. Oh, frick. I don't know. Frick. Okay. But, yeah, now what do I do? Something like that. I go here, then they have a chance to counterattack. But I think it is the move. Maybe you go here or something. What? Nah, friggin', I don't even care, mate. What? Sack the rook, surely? Bruh, I can't be bothered. What's the move? Oh, the knight was hanging? Mate, I was going for a mate. Whatever. Of course it's a material puzzle. I hate material puzzles. Okay, time to do some actual work. So I've done communicable entities in range. Now I have to do send file. Send file is kind of messed up. This is useful for 2C, cool. My transferring file transfer process can be measured by looking at get info, which contains a map. You can only transfer files to entities in range. Calculated separately each tick. File doesn't exist from ID or the file has a finish. I should throw virtual file. File already exists to ID or is currently downloading the target. Should throw virtual file already exists exception with message equal to the file name. Max files reached. You'll find all the exception classes in one place. Exception for the case that the entity is out of range of since you can assume that all entities will be in range for at least the first minute. Huh? What do you mean they'll be in range for at least the first minute? Oh, 2C is the last part of... Oh, okay. Let's see. source entity get what do we from ID dot destination. I just say dest entity. How do we know? Is there like a list file? Add file, get info. Check file not found. Check bandwidth. Check file already exists. Then we check file no storage. Okay. How do we check if file is not found? So if file so if source entity dot, is it like get files? Get type, get speed, get files dot contains key source entity contains from ID and we can have exceptions out there. Huh. Can I just do that? Something like that. String message. Okay. And the message should just be the file name, right? So, how is a band, what the frick is bandwidth? Can receive 1 byte per minute and can send 1 byte per minute, meaning it can only transfer 1 file at a time. What? Teleporting satellite. There's a linear speed if a file transfer can receive 15 bytes per minute and can send 10 bytes per minute. We can say if wait, so we can have like a source entity bandwidth. It's like get available bandwidth or something. Ew, I hate that naming. Get available bandwidth. I don't know. Wait, what? That can't be right. It has to be a different way. Whatever, I'll just leave it now. Yeah, whatever. File already exists? If file already exists on 2ID, okay, that's like they already exist and found not found is not bad. You just do dest entity dot get files dot contains key file name. Wait, what? We have the file name? But like we don't have the file content? Oh no, because the file's already there. You're just referencing it, okay. Check file storage. So should throw with message equal to whatever satellite has too little bandwidth. Oh, okay. I should do two separate if statements. Honestly, so this would be the source. Wait, does 8 bytes per minute mean 8 files per minute? So confused. Cause, mate, I have no idea. Oh, okay, I haven't read this. I can store an infinite number of files and upload and download files from satellites. Files are represented simply by just a string representing their content and a file name. File size only relates to the content of the file and not the file name. Okay, to send files, the target needs to be within range of the source, but the source does not have to be in range of the target. Okay. Source entity dot can connect to dest entity. It doesn't say to throw anything. Do I just return then? Wait, how does it work? If the device is devices aren't limited on number of downloads of uploads they can do. If a device goes out of range without a turn. Sending speed and receiving speed at different transfer rate is bottlenecked by sending speed / receiving speed. Can receive and can send. Can receive and can send. Can store for 3 files or 80 bytes, whichever is the smallest for the current situation. What the frick? Man, I don't even know how to do this. For real, for real. Whatever, let's just do this. And it's satellite. Receive 15 bytes per minute. Can send 10 bytes per minute. cannot store any files that has no bandwidth limit. Should I have like a max number of files for satellites or something? Actually, yeah, who cares about bandwidth for now? We'll just do max number of files. Max files. Bytes per minute. You have abstract variables? Huh. I could have like a file sending interface. It's not allowed for variables, mate. Unlucky.
I'm gonna grab some food actually. Whatever. Can send file. Should can send file take in a file? Can store. I think I really need to refactor my thing out. Satellites have a set amount of bandwidth for transferring files. and a set amount of storage.
So they all should have a storage and a bandwidth, technically speaking.
So if it's sending or receiving, satellites can download from other satellites, alright. Bro, what is this friggin' app? Can I delete all of the devices? What are the settings? Is it a cookie? It's probably in the cache there. This one, it has one cookie. Clear data. Yeah, bro, what a dumbass way to do it. Okay. So let's make a device. Got a H device. And I got a standard satellite A. Got another standard satellite B. Okay. Send file. Oh, but you can't send any files. Interesting. So you can only make files inside here. So we'll have file 1. So you can't send files. So you can send file 1 to satellite A, scheduled to be sent. Open file. Issue file not found exception. Oh. So it doesn't have the file if it's still downloading. Let's get 10 minutes. Send file, scheduled to be sent to B. So does this have file 1 anymore? It still has file 1. What? Does it make a copy? Seems like it. Files are copied.
Yeah. Sent.
How we wasted in dying world. Bruh. No, whatever. Since I'm eating, might as well just watch a lecture or something. Can't be bothered to code and eat at the same time. Comp 259, not watching lectures for 2511. We have a midterm exam? Oh, frick. Okay. There's no way two people are doing it in C. What a troll. The lectures. What?
Of signal processing and heavy maths that's more suitable for the electrical engineering students. If you are really interested in physical layer, there are some nice courses from electrical engineering you can enroll. But here in this course, which is an introductory to computer networking, we are not going to go into physical layer. So that leaves us kind of 6 more weeks because we have 9 weeks and 1, 2, 3, 3 more layers. So roughly about 2 weeks per layer. So that's a good timeline if you like, and I'm comfortable with that. So I don't see any major problem. But today we want to finish the application layer. So if you look at the application layer, we have covered HTTP, web browsing, which is very, very popular and very useful in the internet. And then we have looked at email, briefly, not in
We looked at email.
We have seen that you have server and client for both of the HTTP and SMTP. So HTTP is the protocol, application layer protocol to support web browsing. SMTP is the application layer protocol to support email, right? And both of them are based on client and server. These are the application layer protocols, very popular. But today, we are going to look at another application layer protocol called DNS. By the way, Monday was holiday, but I recorded a lecture for you, and it's uploaded, so you should be able to see that. And we covered in that recorded video P2P, which is peer-to-peer, rather than client-server, strictly speaking, and also socket programming, right? So today we will try to focus on DNS and a little bit from CDN, content distribution networks, which uses DNS. So if we can finish DNS today, we should be happy. Right, so DNS is something that the users at the moment in the internet do not use directly, like email or web browsing. It doesn't have any direct interface with the human users, right? DNS is something which sits in the background. It is application layer protocol, but it's not used directly by human, but it's used by other application clients, such as HTTP, SMTP, and other application clients in the background. And I'll explain to you shortly why. However, DNS is not a transport layer protocol. You might think that, oh, if application requires some services, it should come from the bottom, right? Transport layer, such as TCP or UDP. But DNS is not a transport layer protocol. DNS is an application layer protocol. So going back to my drawing here, this is very useful. This is a stack, and you need to know which one is here. So you can see we have studied HTTP. We have studied SMTP, and now I'm saying that HTTP and SMTP both makes use of DNS. And you might think, oh, DNS is transport, but it's not. So all of these are application layer protocol. Okay. So why DNS is used by HTTP and why SMTP needs DNS? One thing, it will become clearer to you later as you study TCP and UDP. But by now, you already have used sockets, right, in your lab. Okay. So socket, if you open a socket, for example, if you open a TCP socket, then you have to give it the IP address and you have to give it the port number. So for HTTP, for example, the client, the browser, wants to set up a TCP connection with the HTTP server. Right? We have seen that delay. When we try to formulate the delay encountered by HTTP, we have said that the first thing you need is to set up a TCP connection, which takes a round trip time, right? So how do you set up a TCP connection? You open a socket, right? And you open a socket, you have to give the destination IP address, right? So HTTP destination IP address, there is something missing, right? So if you look at HTTP, then you see strings like HTTP :/www.csc.unsw, these kind of things. But this is okay, this is good. I want to get the web page from that server, this is fine. Except when I want to open the TCP connection because I need it for my HTTP client, I find that this is not enough. Right? I need to supply the IP address of that web server before I can get the page. So you see something is missing. Something needs to be resolved before the HTTP client can get you that HTML page so that you can see everything on the web page. So in the background, what it does, it resolves the name, the domain name, the HTTP URL, to the correct IP address, 32-bit IPv4 address. And how does it resolve it? So that's DNS. So in the background, it uses DNS. DNS stands for, who can tell me? DNS is another acronym. Remember, I said that there are thousands of acronyms in computer networking. DNS stands for domain name service. Yeah, it's a service. It's an application layer protocol. So if you give it a domain name, such as www.csc.unsw.ac.au, then it can tell you, oh, it's this 192. Blah, blah, blah. Right? Email is the same thing. You're trying to write an email, right? And how do you write an email? You say mahmoud.hasan@unsw.edu.au. Okay, I want to send this email to this person. But you have to send, your SMTP client has to take this email message and start a TCP connection with the SMTP server of this destination person, right? And again, it needs the IP address. So again, the same thing. SMTP wouldn't work if there was no DNS service running in the background. So you can see DNS is a very powerful service that supports HTTP, email, and all the other application layers that needs to open a socket. And everything needs to open a socket. And if you want to open a socket, you need the IP address of the destination, right? So DNS is very, very useful. And today's lecture is about understanding how exactly DNS works. At one point, I might have told you that TCP is the most complex software in the operating system, which is true. But TCP is like in the kernel of the operating system, right? Above the operating system is the application layer. And if you look at all these applications, DNS is probably one of the, or maybe the most complex software. You don't see it, you don't interact with it, but like HTTP is just sending a request when you get the object. HTTP sends the file, and then email you just send the file. But DNS, you see, to resolve is not that easy. It's very complex. But in the lecture, we'll try to get the gist of it and try to understand it. And then in the lab, you are going to use some tools that are the practical tools that implemented this DNS, so you can use it and you can see how it works. Right? You collect some data about some DNS experiments, and it will become clearer to you. Right? So if you look at the services that DNS provides, you can see. So service 1, 2, 3, and 4. 4 main services. I'll explain them. But these two services are about aliasing.
No distribution.
The first one is clear, right? Host name to IP address translation. So you have the name, so domain name like csc.unsw.edu.au, it's like a name. Then you want to find IP address. Okay, that's fine. What is aliasing? So aliasing is also interesting because when you go to the name, you see that the name can be very long, right? For example, wagner.csc.unsw.edu.au. Even the name can become so complex, you can't remember it. So you want a simpler name. And then from simpler name, you have to get the longer name, which is the real name. And from the real name, you have to get the IP address. So there are multiple levels of resolving, right? So if someone's name is very long, also for human, we have a nickname, short name, and we remember it. But then we need to know the full name because the full name is needed in certificates and announcements and places like that. And then you need the address, right? So aliasing is very useful, and you will see that there are two kinds of aliasing in DNS, right? So this is where many of us confuse it in the beginning. So there's a specific aliasing for mail because mail server is very important, and there's so many emails going on in the internet. So mail server has its own aliasing, and the rest of the other servers uses the other aliasing. And when I say rest of the other servers, predominantly it's the web server. So web server is very important, mail server is very important. So if you're going to set up a service, a digital service, and you want an online presence of your company, then the two things that you have to establish very quickly is web server and email server. So people can contact you and send their problems and requests and feedback by email, and web server is to get the payments and the products, advertisements and things like that. So we'll see two kinds of aliasing, and we'll see what are the constructs available in the standard DNS to solve them. Okay, the fourth one is interesting, important, and becoming more important because of the scale, the way the internet is growing. So there are like practically millions of queries for web pages coming into big servers every day. And if you just have one machine, no matter how many core CPU and GPU you have, that server, that physical machine server, cannot cope with that, right? Because there are too many TCP connections. Everything needs TCP connections, and TCP is stateful. So once you have a TCP connection, if you have watched the lecture note, the lecture video from Monday, then where I explained to you that there is one TCP socket that will be dedicated from the server to every single client. So if there are 1,000 clients coming in at the same time, it has to maintain 1,000 TCP connections. So it doesn't scale very well. But at some point, the server becomes the bottleneck. It's not the propagation delay, it's not the bandwidth, it's just the computing power of the server that becomes a bottleneck for your page download time. You don't want that because machines are, you can buy more machines and you can divide the load to many machines. But you don't want to tell the users that I have 200 machines and then they have to remember these 200 names. So you just have one name, say that my web server is www.unsw.hw, for example. But in the background, we may be running 10 servers at UNSW. They don't need to know that, right? So that's called load distribution. These 10 machines connected to the internet will require 10 unique IP addresses, right? So they will have different IP addresses. So you can see we are kind of doing aliasing and load distribution. So from one name, we are giving to multiple physical machines so that different machines will take part of the load. So this is load distribution. So DNS, you can see, not only useful for solving the IP address, resolving the IP address, it's also useful for proper functioning and managing load for large organizations or organizations that become very popular. And you might have guessed already that it's not possible to centralize the DNS service. You can't say, conceptually you might think, oh, I will have a very big machine somewhere in the internet that will have the mapping for all the names to their IP addresses in a very big file, and then everybody can send a query to the server and we get the DNS. So why I need to make it so complicated and we need a separate lecture on DNS. The amount of DNS queries is just huge, as you can see here. Comcast is another in the US very popular, like Netflix. They get more than 500 million DNS queries in their DNS servers because people want to watch movies. They click the URL link of the movie and all these things, which will show you how it works. But they have to resolve these DNS queries, load balancing, and all these things. So just one machine, just from the traffic point of view, this is not just practical. The other problem is if that server crashes, then whole world, the internet will stop, right? So it's a distributed thing. So you'll see that anything that is distributed is more complex than is centralized, right? So we have to understand how the distributed system solves the DNS name resolving problem so efficiently, right? So that's the topic. Okay, there are some goals. So when you want to name, the names should be unique, right? So if you have the same name, then you don't know which one you are trying to resolve, right? So how do we have the uniqueness in the name? In the scale, we talked about the scale, and it has to be distributed, and also we want it to be autonomous. Like autonomous, in the internet, everything is autonomous. It's a network of networks, right? All these small networks are autonomous. They have different administration. For example, this university manages its own network, so we'll manage our own DNS. So all these machines, like this machine that I'm using for the protection, it has an IP address, it has a name, right? All this should be managed by autonomous DNS service located here at UNSW. Yet, it should be connected to this distributed system in the world, so anyone who is looking for the IP address of our machines will be able to get this one very quickly. So it has to be autonomous, right? And highly available, of course. Like if something is down, one machine, it should still work, otherwise the internet will stop. And it should be fast. Okay? So when we studied HTTP, we focused on page download time, right? And that was our performance metric because the users want to download it very quickly, right? But as you can see in the background, it's actually using DNS. It needs to resolve the DNS name to IP address before it can open the TCP connection, which we have not shown you when we studied the delay. We just say it is round trip time and things like that. But in built, there was delay caused by DNS as well. So if DNS takes lots of time, then all these applications will suffer. And that's why DNS needs to be extremely fast. Right? So these are the goals of designing the DNS system, and we'll see how the distributed DNS works in the internet, and yet it works in the internet so smoothly, and yet addresses all these issues. So there are a few concepts that we have to go through. The first one is hierarchy, right? So if you want something autonomous, if you want to maintain uniqueness, and if you want to make sure that it's distributed and fast, then you need a hierarchical system. Flat systems are not good. Flat systems means you have to sequentially search the whole thing, right? Hierarchy is very fast, and that's why if you're a computer science student, you know that we have so many algorithms, binary search, tree search, all these things, these are hierarchy. So no wonder DNS follows a hierarchical system. So that's the first concept. How the DNS hierarchy look like? How does it look like? How does it work? These are the two things. Okay, so if you understand that, then you understand the first concept of DNS. So pay attention. This is a very important topic, both for asking questions in the exams, doing the exercises in the labs, and this year, as if the time permits towards the end, I'll talk a little bit about the assignment. This is week 3, and I promise to release something on the assignment. The assignment will be coming from DNS. So pay attention, ask questions if it's not very clear. So we'll do, okay, so first thing, the hierarchy. So namespace and administration, both are hierarchical. So I'll explain what I mean by hierarchical namespace and hierarchical administration, right? And it's the servers that are hierarchical. Let's go straight into the picture. And what you can see the hierarchy here. So there's just a root, so don't worry about it. But then you have these domain names, right? Some are based on these categories, such as educational, commercial, government, military, these kind of things. And the other categories are like the country-specific geography. So here you can say UK, France, and things like that, right? And if you go under education, then you see all the universities, education institutes, such as University of California at Berkeley, University of California at Los Angeles. And it's like a tree, and then their electrical engineering and computer science department, and then under that some more. So you can see it follows. And the domain name, when you try to write the domain name in dot form, you basically add these dots, right? And then you have the name, but you can see this is hierarchical, and namespace is hierarchical, right? So if you are an educational institute, definitely you will come down from this edu, right? You will not come from government. So the namespace is hierarchically follows a hierarchical name. Was there any question? Just raise your hand if you have a question. And administration is also hierarchical. So this slide shows you that autonomous and hierarchy. So for example, these green lines are basically your zone. So this is, in this case, UCLA is one zone. Here, Berkeley, one zone. Here, this is another zone. So every zone needs to have its own name server, which will look after that zone, right? So you have one machine which will be responsible only for one zone. So how you decide the zone is up to you. So in this case, we can see the same institution, such as University of California, will have many zones, and it means it will have many DNS resolver, DNS name servers. It's called authoritative because that one is the formal authority for telling you what is the name and storing the authoritative records of which name is mapped to which IP address. So every zone will have an authoritative name server. So NS here is name server. So we'll have a machine here. Have a machine here. We'll have a machine here. So these are like authoritative name server. Authoritative name server. Authoritative name server. This is autonomous because this authoritative name server is under the authority of this administration, right? So someone here will have no control over this, right? Is that clear? So authoritative name server is a concept in DNS which says that this name server will have the authority, and this is the most valid answer. So if it comes from this server for this IP address which belongs to this zone, then you know that this is the truth, right? And later you'll see that in the communication there is a flag in the packet which says it is coming from the authoritative server or not. The reason that it may not come from the answer authoritative server is because of caching. So caching is something that we'll deal with later. Okay. Okay. So this is another terminology. Top-level domains, or TLDs, right? So anything after the root immediately are top-level domain, right? So COM is a top-level domain, edu is a top-level domain, right? And these are big. As you can see, top-level domain, like edu, is such a big, there are so many institutions in the world, educational institutions in the world, and they all come from this top-level domain. So what are these top-level domain? What kind of administration is needed for this top-level domain? What's the difference between authoritative name server and the TLD name server? So they also have machines. So every top-level domain needs to be managed, and they will have a machine, a DNS name server, which will help in this distributed name serving process. So what's the difference between authoritative name server and the top-level domain name server? TLD versus authoritative. What's the difference? Okay, and there is a local. So basically there are three concepts: local, authoritative, and top-level. So authoritative, as we just discussed in the last few minutes, holds the actual records that maps a name to the number, right, for that zone that this authoritative name server is responsible for. Right? TLDs do not hold those records, but they can tell you the address of the authoritative name server for a given name, because you don't know who is the authoritative name server who can give me the answer. So, but these TLDs, name servers, they are publicly advertised because there are not many, right? Maybe a few hundreds, right? TLDs. So these TLD domain name servers are publicly advertised. You can go and find the IP address, right? So if you don't know the authoritative name server, in the beginning you don't know. So you can go to the right TLD. For example, if you're looking for a name, csc.unsw.edu.au, then you know that the top-level domain is edu, and you know edu, they have advertised that there is a machine, a name server, which is a TLD name server for edu, so I should go and ask it that, can you solve my problem? And it cannot directly solve the problem because it doesn't have the records, but it will tell you, oh, go to that authoritative server. So the TLDs maintain the list of all the right authoritative servers. But They do not actually hold the records that map the name to the number. Right? If you don't know the TLD names, of course you can go to the root.
Why does it say titanium? Oh, they just added their own. What a troll ass image. Whatever. Oh.
knows all the TLDs, right? So you can first go to the root, and then the root can tell you which TLD you need to contact. Right? All these things will be clearer once we... Okay, so the root is somewhere...
Honestly, it's probably better to just screenshot this.
can always go. And it's replicated throughout the world. And as you can see, like in the east coast of Australia, we have 17 root servers. And these are replicated. And there is a website, you can go here, right? And you can find out the IP addresses of all the root servers, right? That's closest to you, for example. And you can configure your machines in your network so that they can always go to the root, right? If they don't know anything. That's the simplest. So you go to the root, and root tells you what's the TLD, and the TLD tells you which name server. Once you go to the name server, you will get the answer. So that's the hierarchy, right? I would like to go quickly to a picture to explain you the process. And then all these elements will be clearer to you because this picture has root, this picture has TLD, and this picture has a local DNS server, and this picture has authoritative. You can see this picture has everything, and this picture has a client as well. So let me just use this and show you step by step that a distributed domain name service is used to resolve the name from the client. Okay? But there are two different ways to do this. And the first one, which is the preferred, is called iterated. And I'll explain what we mean by iterated. Okay, let's start. So this is your client. Okay, this is a user device. So user is sitting on a desktop or laptop, mobile phone, iPad, right? And you are trying to browse a web page, right? At engineering.nyu, New York University.edu, and index.html. You want to download that index.html file, for example, right? But you need the IP address because if you want to download an index.html, the first thing is just open a TCP connection, and TCP connection opening means you need the destination IP address to give it to the subject so it can do the three-way handshake and open it, right? So the first thing your user machine needs to do is to find out what is the IP address for this, right? You are trying to resolve that, right? What's the IP address for this? So you send this query to a local DNS server. So what is a local DNS server? So it's a DNS resolver sitting right here in your network. Okay. So if you are at UNSW will have a local DNS server to resolve the queries from any machine. So in the lab, when you say, you write a command in your program such as get host by name, it sends to the local DNS server. That's the first port of call, right? And you're hoping that this local DNS server will give you the answer, right? So the query always goes to the local one first. So that's why step one, it goes to the local one. So caching is a very powerful concept in every layer. So when we studied HTTP application layer, we looked at how caching is used in HTTP, right? Now we are looking at caching for DNS. So you are getting so many queries, right? Hundreds and thousands of queries every day. It's a large organization. And then each time you want to grab it from the root servers, from the TLD servers, from the authoritative servers, you're creating lots of traffic and also there is delay, right? But if it's a popular destination such as a Google web server that everyone is using, then you should cache it. So if you cache it right here in the local, you can cache the answer. Then it can give you the answer later on, but you don't need to cache, right? So it can't find the answer in its cache. So iterated query means this local DNS server doesn't tell the user that, sorry, I didn't find the answer. You try something else, it's not my problem. It doesn't tell you that. It takes a request and it says, okay, let's see if I can find the answer, right? So what it does in step 2, goes to the root DNS server because in the beginning it doesn't know anything about the TLD servers. Right? It doesn't have any information about the TLD in its cache. So if you don't know anything, at least you know the root because the root are published and you configure them when you install your network. Right? So it has access to multiple root servers. It can try one by one. So it just goes to one of the root servers. So that's step 2. The root server says, oh, you are looking for edu, fine. Go to this TLD server. So step 3. Root server sends a response to this one saying that your TLD server is this one. Go to that TLD server because that TLD server is handling all the edu related authoritative servers. If you ask that TLD server, it can give you which authoritative server you should contact. So in step 4, this local DNS server contacts this TLD server, and this TLD server responds with the IP address for the authoritative DNS server at this New York University. Okay. Oh, sorry, actually, you were trying to resolve this one. And this is where you are sitting. You are sitting at New York University and you are trying to resolve this machine, which is at University of Massachusetts, right? Using another network. Okay. So once you get the authoritative DNS server address at UMass, then in step 6, you contact this authoritative DNS server giving this name, gaia.cs.umass.edu. Can you tell me what's the IP address? And he says, yes, I know the IP address because this is the authoritative server, right, for that zone. And it has all the records in this file. Remember, authoritative server has all the mapping. So it gives the answer. So in step 7, then local DNS server solves the problem, resolves the IP address for this name. Instead 8, it gives to the user. And the user thinks, oh, my local DNS server was capable, and it was very quick, maybe 3 milliseconds, maybe 100 milliseconds or something. So this is something you will work in your lab. You will try different destinations and you see how long it takes, what's the statistics. So the problem is solved. It's called iterative because you can see it's not solved in one go, but it takes many iterations. But those iterations are done in the back, and the user, or the resolver in this case, so this is the local DNS server, you can also call it local DNS resolver, it iteratively contacts multiple DNS name servers in succession to find the answer. That's why it's called iterative. But at the end, the problem is solved. Any questions so far? Yes? Do you want to use the microphone?
The authoritative DNS server has the mappings for that particular organization, right? I mean the particular zone for which the authoritative DNS server is set up.
Yes, so this authoritative DNS server, which is dns.cs.umass.edu, is for this University of Massachusetts. So it's looking after all the machines, including this machine.
Okay, so can this server be used as a local DNS server for University of Massachusetts?
Yes, so if there is, it's a good question. So if there is another user, right? And then it needs a local DNS server. So it may be the same physical machine, right? So it has the authoritative DNS server. It can also run a local DNS server if you want. Or it can be a separate physical machine, right? So this can be your local name server, right? So it contacts this one first, right? And it will find it in the cache. If it doesn't find it in the cache, then it will probably find it in the cache that the authoritative DNS server is here. So it can go here. Like, yeah.
One more question. Yeah. So the local DNS server, so if I'm using my own Wi-Fi at home, and this local DNS server, it is part of, who sets it?
Yeah, so if you are, all the examples I've been giving you are like enterprise, like UNSW and things like that. Now, your question is about residential user, right, at home. So at home, you are connected to the internet via an ISP, for example, Optus. So you are just one customer of the Optus. So if you're a residential user, and Optus, for example, right, is your ISP, then you are connected to the Optus network, right? Many people are connected. So they will have a local DNS name server. So if you are here, then you're connected to Optus network. And if you want to resolve something, you'll be using the Optus's local name server to resolve the query. And if that ISP cannot solve it, then they have to go iteratively to the root server. Okay, any other questions? There's a lot of things in this picture, but the steps are very important for you. How is solving the problem? In a distributed system, you can see the system is highly distributed in terms of autonomy, in terms of physical infrastructure, and everything. Okay, is that clear? So I take it that it's reasonably clear. You might have questions later, but you can go back and read the textbook, go through this lecture recording again. But the other thing I want to show you is that the problem with the iterative is that your local DNS server becomes very busy, right? It goes to the root, then it goes to the TLD, then it goes to the authoritative root, right? To find the answer and then solve the problem. If there are a lot of queries coming to the local DNS server, if there are hundreds and thousands of users in a large organization, then local DNS server may be very busy, right? So there's another option called recursive. This is the same thing kind of, but it works in a different way. It takes the load away from the local DNS server and puts the load on the other servers. You can see in step 1, it doesn't have the answer. So in step 2, it goes to the root server. But see, root server is not asking it to go to the TLD server. Root server takes the responsibility recursively, and it goes to the TLD server. TLD server then takes the responsibility, and in step 4, it goes to this authoritative server. And once it finds the answer, it gives the answer to the root, and the root gives the answer to this one, and this one comes back. So this one is not overloaded. So this time, our local DNS is not overloaded. However, who is overloaded? Root. Very good. So this is the trade-off, basically. The root servers, they get so many queries, they don't want to be overloaded. So, and also you can see the TLD servers are also overloaded because they have to recursively solve the problem, right? They're also loaded. If you like, overloaded. Okay, so you can shift the load from the local DNS server to the outside. Right? So if you allow me to draw this boundary, this is the local boundary, right? And this is the internet. So you are shifting the DNS load from the local name server to the internet server by using recursive options. Recursive is another option, right? But if you use the iterative option, then the load is shifted from the internet to the local machines. These are just two options. And not all internet name servers support recursive. If they don't want to be overloaded, they don't support recursive. So you have to use iterative in this case. So you try something and don't find the answer, you have to, they will not solve the problem for you. They will come back to you and say, here's the TLD server, go and do it. I don't support recursive. Okay, so any questions? The difference between recursive versus iterative. So that's another concept, and easy to confuse, and wondering what's the difference. They look so same. If you just look at these two pictures, they appear to be very similar, right? So what's the difference between recursive and iterative? Is that clear? Do you have any questions? Any hands anywhere? No. Okay, so very clear. That's good, right? So that brings us to caching. So caching is important because as you can see, there are so many steps, and it increases delay because there are some round trip time, right? So by using caching, you can significantly reduce all these steps and solve the problem in a single step, for example, right? If there is a popular destination, then you can cache it. The problem with the caching, as you have expected, is the stale information, right? Maybe it's not valid anymore. Maybe the information has changed. This mapping has been changed by the alternative server, and we don't know that because we've been caching it. So how long should I cache? In DNS, there is a specific field in the packet header called time to live, TTL. So that TTL tells you how long you should keep it in the cache, and after the TTL expires, you should expunge it from your cache. Delete it, right? So the authoritative server sets this value. So I set my record saying that this name has this IP address, but when somebody asks for the information, I give the information, but I also tell it, do not cache it more than 20 seconds. Do not cache it more than 2 days. Do not cache it more than 100 days, because the authoritative server has this knowledge how volatile that information is, right? Then when you cache has always, nothing is infinite, right? Cache is also finite. If everything is popular in this world, then the cache will be full very soon. And as a local cache manager, you have to make a decision. How do I manage the cache so I can fit more information in the cache? You have to delete some information. Which one you want to delete? So there are many caching algorithms, right? And different algorithms will perform differently depending on the traffic, right? So caching is an interesting area which can impact the performance of computer networking as well. And maybe you can explore these things in your assignment, because the lab has very specific exercise, but in the assignment you have more over the weeks, many weeks. So we can do that in the lab. Okay, so I think this is a good time to take a 5 minutes break, and when we come back, we are going to continue with DNS and try to finish it today. Just 5 minutes.
Oh my goodness, I'm so full.
So we are back. Please take your seats. We are going to resume the lecture. And as we said, caching can be very useful in reducing the number of steps involved in DNS query resolution, and that can reduce the load in the internet. It can reduce the time to resolve. So you can cache the TLD servers. You can cache the authoritative name server, so you know where to go. You can even cache the actual mapping, so you are kind of like the authoritative server, and you can quickly give the answer. Right? What is negative caching? Now this is also useful. So sometimes the users type incorrectly the name, and that name doesn't exist. So at the end, you go all the way to the name server, and the name server says, "Sorry, I cannot find the IP address for it." Right? So you don't want to do that many times. So if it's incorrect, you can say that it doesn't exist. So that's a negative cache. It doesn't have an answer, but it knows that there is no answer for it. Right? Okay. So that brings us to another important concept called DNS records. Now you understand how the distributor system and the hierarchical system works. You know the difference between iterative and recursive to resolve the mapping. And now we are going to look at the records that are stored in the authoritative server and how they control these multiple levels of mapping, such as aliasing, right? You have aliasing and you have the direct mapping, but how does it work? So if you look at the records, it's not just, oh, here's the name and here's the IP address. It's not just like that. There's only one type of record, so that's called type A. It's the simplest one. So you have a host name and it's mapped to the IP address. Good, very simple. But if you want alias, multiple levels of abstraction, then you need the other one. So the type NS is the authoritative name server, right? Is the authoritative name server. So the TLD domain, remember that TLD is the top level domain name servers. They should be able to tell you who is the authoritative name server you should go and contact, right? So this NS record can be stored in the TLDs, for example. So the TLD will not give you the IP address of the domain name that you're looking for, but they will give you the IP address of the authoritative name server who can give you the IP address of the name that you are trying to solve. So how does it work? So you can see there is 4 parameters: name, value, and type. DTL is for caching, right? So we are not going to worry about it right now. So there are 3. So this type, if it is A, then this name and value, name will be the host name and value will be the IP address. If this type is NS, then the name will be the domain name that you are trying to find the IP address for, and the value will be the authoritative name server's IP address, the host, the name of the name server that you should go and look up. And if it is CNAME, so this is for aliasing for the canonical, it's a long one. So then the name will be the long one, and the value will be the long one, and name will be the short nickname, right? For example, this is the short one, right? This is the name, and this is the long one. So this gets the value. And if remember we said that main servers, they have specific alias for main servers, so that's MX. So if your type is MX, then you get the long name of the main server associated with the short one, which is the name. So the name may be just unsw mail.unsw.edu.au, but the main server will be maybe the Wagner or CSE name 2 and all these details. So if you so the main thing is here is that the type dictates what you should look for in these 2 variables. So if you create a table, and if you say, okay, type is here, and I have 2.
Is it drawing with his mouse?
Value and name. Right. Then you can say, okay, there are 4 different types. So if the type is A, now it's your turn. You should tell me what would be the value and what would be the name. So what's the value? IP address, yeah. So it's the IP address. And name is the host name. And interestingly, you will see that this is the only type with this IP address. So if it is NS, who can tell me what's the value? So value is the name, right, of authoritative name server, right? Authoritative name server, that's the value. And the name is the domain. So you can fill out the others, and by doing this exercise, you can see how the type controls. these two parameters, value and the name, because this is how you have to decipher the contents in your DNS record, right? And these will become even more clearer once we do. Okay, so this is the format. You have to go and understand the format well. If you're going to implement, you have to understand the format. But it's best to look at an example. So here we have a case study. You are setting up a new network, right? And you want your presence in the internet. The first thing you have to do is set up your DNS server. Because if you don't set up your DNS, nobody will find you, right? So you want online presence. The first thing, what do you do the first thing? DNS, how do I do it? So this company is called Network Utopia. Sorry, not Utopia, it's Utopia. Okay, networkutopia.com, right? So you want to be under .com. So what do? You register, you go to this TLD. So Network Solutions is managing the TLD for .com. You go there and you say that I want a new name called Network Utopia. So they will check that whether this is unique, because they are managing that TLD. So they can say, yes, you can have utopia.com, it's unique, nobody has registered that name yet, right? So the name registration goes through the proper registration, and then once this is accepted, unique, then comes the DNS. So what you have to do, so you can see you have to do NS and you have to do A, two records. Why? So this is NS. So remember, now we are not showing the TTL, don't worry about TTL, but if the type is NS, remember, if you go back, if the type is NS, then the first one is the domain, and this is the name of the authoritative name server, the second one. So the domain is networkutopia.com, and you are saying my authoritative name server is this. This is your authoritative name server. Authoritative name server, right? For your company, you say that the name of my authoritative name server in my company is dns1.networkutopia.com, right? So if someone comes to this TLD saying that, you know, I'm looking for a hostname in networkutopia.com, then you say, oh, go to this dns1.networkutopia.com. But what is the IP address of it? And that's why it will store an A record as well, which says that this is the IP address. So what do we see here? We see that two records are needed to be stored in the TLD so that the TLD can respond saying, go to this authoritative name server. By the way, here is the IP address of the authoritative name server. Right? It cannot be stored in the same record. It's because every record has a type. And in this case, you need these two types. Once this is done, so this is the registration. When you say I want to register, you say this is the name of my domain, and they will check whether this is unique. And when this is unique, they will ask you, what is the name of your authoritative name server? What is the IP address of your authoritative name server? Once you give this information to the registrar, they will store that information this way. Okay? They will store these two records, DNS records, in their TLD server. And you are kind of done from the registration point of view. Still, people will not find you yet, because they will then come to your DNS server, and then if you have not configured your authoritative name server, they will not find anything, right? Yet, but at least you have done the registration properly. So the next step, so this is step 1, you do the registration and the TLD configuration. Step 2, you have to know your authoritative server. Remember DNS1, and this is the IP address, right? So you have to
indicate that the authoritative name server.
to create a type A record, right, for your website and email. So this is website and this is email. Remember, these are the two most important applications. So for web, you can say, if somebody is looking for www.networkutopia.com, then they will find what is the IP address, right? So you have to set a type A record, and you are saying for the mail, right, you have to set up an MX record, so you can use this alias, right? So this is an alias that you can use to set up the mail. So now, if you do all of these things, then let's do the reverse. Now we are saying that you're all set, right? So now let's see how someone in the world can actually download a page from your website, right? So when they click on a URL, right, we may be saying www.networkutopia.com/index.html. They click on it, right? But that page needs to be downloaded, right? So an IP address is needed by the HTTP browser to actually open a TCP connection to the web server of networkutopia.com. So they need the IP server. So what do? They can go to the root, right? And the root will say, oh, you are .com. Here is the TLD server for you. Just go to the TLD server for .com. So they will go to the TLD server. And they will say that can you give me the IP address for www.networkutopia.com, right? So this is the query they will send to this TLD server. So you come to this TLD server and they will say, oh, your domain name is networkutopia.com. So I do have an entry for NS, right? It says if this is the domain name, that the DNS authoritative server is DNS1 dot blah 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 blah, and this is the IP address, right? So you should go to this IP address to get the IP address for www.networkutopia.com, right? So it sends a DNS query to this one, right? Because this is the authoritative name server's IP address. So it sends a DNS query to this one saying, what is the IP address for www.networkutopia.com? Fine. When it comes here, this one has a record for this. It means it has a mapping, and you can say, oh, here's the IP address for the web server. And once you have the IP address for the web server, the TCP socket can open a TCP connection to that server to get that index file. Okay? So I just explained it verbally. So do you have any questions? Do you see how it works now? So you have to convince yourself that yes, people can navigate to the web server of this company as long as I configure the TLD server and as long as I configure the authoritative name server in my company. So I leave the MX, the email, how they will find the email server as an exercise for you. Okay, MX. Any questions before I move on? Yeah. Can you speak to the microphone? So
Assume I only have one physical server, a physical machine, and I want to use it at my DNS server and my web server at the same time. Can I just navigate to localhost to get to the web server?
Okay. Yeah, it's a good question. So can I use the same physical machine for web server and my email server? The answer is perfectly yes. In many cases, they use the same machine to run multiple servers. In that case, the IP address will be the same for the main server and for the web server. Doesn't matter. They can connect to that server. The port numbers will be different. So for the web, it's 80, and the main will be something else. So the TCP connection will still work. And same as the DNS server. Yes, you can still use that. Yes, you can run all your servers in one machine if it's a small flower shop. And it doesn't have a lot of machines or a lot of power supply, a big server room, and not a lot of clients. It just wants to sell some flowers through internet payment. You can just have one machine and load all these servers. You know, Ubuntu and Linux, and you just run it. And they have all these servers, so you can run all these servers in the same machine. IP address is the same for all of them. Doesn't matter. Yeah, good question. Anything else? Okay, so you know that the DNS servers are replicated. We've already said that. DNS uses UDP. So UDP means that the packets can get lost. So they use sequence numbers. So in the packet header, if you remember, they have identification. So you send a query, and there's a number for this query, and when you get the response, it copies the identification. So you know that you have received the response for the query. If it's, so you know reliability, you have to set up a timer. So if you do not get a response within that timeout, then you have to retransmit. So you have to implement some of the reliability issues yourself. I mean, DNS has to implement that because it's using UDP. Okay. And just talking about some public. So there are some public DNS server, so if you don't want to run your own local DNS resolver, then you can always send it to a public one, for example, Google DNS. You can treat it as a local. You can always send it as the first point of flow, right? So many people do that, and you will spend a lot of money. Very sophisticated caching mechanism, huge server room, and communication power and everything. In some cases, the performance of Google DNS is better than what you can run in your own organization, for example, right? So many people use that. However, the thing is, it's a public one, so all your queries, everything, gets recorded, so they know what you are doing, right? So that's what we are highlighting here. So privacy issues. Okay, so there are some security ones. We are not going into that. Cache poisoning. So remember, if you are caching information, so you either get from authoritative or you get from someone else. So if you get from someone else, which is not authoritative, then maybe you are not interested in that information because they can give you wrong information for some access activities. For in this example, they are just saying google.com is in this address, but that address is actually your network. So you might think it's google.com, but it comes to your server, and then you are giving false information. So DNS is a very powerful thing. It can be used for good things, it can be used for bad things, and a lot of bad things are happening in the internet. They are redirecting the traffic. You think it's coming from the right source, but it's actually coming from a fake source, lots of fake information injected. So DNS is such a powerful thing that not many people outside computer science, they realize that how DNS is actually used in the internet. But this example shows you that DNS can be misused, right? And if it's not from the authoritative server, then you should not pay much attention to the information. Okay, so time for some quiz, just to test ourselves whether we understood some of the basic points about DNS. And then if the time permits, I think I also want to cover very quickly CDN, and if the time permits, I'll give you a glimpse of the assignment. Right? So the first question in the quiz is, we are talking about the local DNS. Okay. If it doesn't know where to find the answer, then what should it do other than trying? So who thinks the correct answer is B? Okay, quite a few people. Who thinks it will ask that neighboring DNS server? No one? Okay. The request is not processed, it will drop it because it has no clue. No one? Okay, good. Yep, the answer is B. If it has no clue, then it goes to the root server. Then the root server will definitely have one clue, which TLD server. Then you can go to that TLD server. Right? We have seen that in one of the slides. But usually you have a clue because you cache it, right? And you know all the TLD servers because that also can be downloaded from the internet. Right? So you can go to the right TLD server directly. Okay, next please. Which of the following are respectively? So the first one and the second one. So the first one is for the client-side ISP, and the second one is the domain name owner, like the utopia.com. There's the domain name owner. So which of the following are respectively maintained? Who maintains what? So the first one is maintained by the client side, and the second one is the owner of the domain. So who thinks the first one is correct? So the root DNS server is maintained by the client side, and the
which of the following are respective by the client side, ISP, and the domain names? client-side IP and domain name one. What's client-side ISP? Internet service provider. So internet service provider would have authoritative names or top level domain. I think it's C.
TLD is maintained by the domain name owner. Who thinks this is the correct answer?
Actually, no, I don't
No
know.
one? Okay. How about Lee? The client side maintains the root, and the owner maintains the local. Doesn't make sense. Good. How about C? The client side maintains the local DNS, and the owner maintains the alternative DNS server. Yep, we can stop here. See, these are all logical now. Now that we have gone through all those pictures, local and the alternative. So that's good. So you got it right.
Well, we'll see.
Okay. So this one is about the type. Remember, there were 4 different types. The question is that you are doing the email program, right? And you want to send an email to me, right? So you say that send this email to here. Your SMTP client needs to create a specific connection with the server of this domain, unsw.edu.au, right? So what kind of DNS query will be triggered by your DNS resolver?
Surely,
A, B, C, D, E. Which one do you think is the correct one?
surely it's E.
Anyone has any idea? Who thinks the answer is A? Yes or no? Why no? Why can't I ask, give me the IP address of this name? Why can't I generate a query like that? Because I do not know the name of the mail server. Mail server's name may be, mail2.csc.unsw.edu, right? I don't know the name of the mail server. So how can I ask the IP address of the mail server? Right? Type A is if you know the name, you just want IP address. Right? So here I do not know the name. I just want to send to the mail server of this domain. I don't know what is the mail server of this domain. I have the domain name. That's good. I want to find out what is the mail server of this domain name. Right? So which one is correct? Which one? E. So one is saying all of the above, but we just say that A is not correct. You can't use A. So the E is not correct. D. So what is D? MX. What is MX? It's saying that if I know the domain name, I can find out what is the name of the mail server. So value is the name of the mail server. Name of the mail server. And name is the domain name. So if you know the domain, you can use this MX query to find out what is the name of the mail server, right? So in our case, the mail server for this domain may be mail2.unsw.edu.au, right? And once you have the name, then you need to find out what is the IP address, right? So you need a query A to find it out. So you will need MX to do that. Okay. Yes? Yeah, caching can be done. So in your local DNS server, you can cache anything that you wish. Yeah. So the last question is, for example, you want to click this in your browser, www.polev.com, right? The question is, how many DNS requests sent by your local DNS server? So your local DNS server is sending DNS queries to the internet servers, remember? Remember this picture? Recursive. Or iterated, so this is your local server, and it sends query, right? In this case, 1, 2, 3. Okay, now coming back to this quiz, the question is, how many? So what would be the answer? What's the minimum number of? Who can tell me what's the minimum?
1.
0. Good answer. Yep, that's correct.
0.
So the local DNS server may not actually send any query message to the internet to resolve this because cache. Yep, you're right. Yep. So now you also understand what is cache and how powerful it can be. Okay, so I think we can say that DNS has been covered. B2P was covered Monday, and I just wanted to cover the video streaming and CDN. So CDN, Content Distribution Network, it needs no emphasis that the traffic, the huge part of the internet is not consumed by video. Netflix, YouTube, Amazon, Stan, everybody's watching all these things, and the video generates lots of packets. If you just want to watch a movie, there's so many packets because video has lots of data. Video takes maybe a second, lots of frames, right? Not like a small text. Say 80% in 2020. So the problem is how do you manage all of these things? So the first thing is a couple of things. So everything is coded, spatial or temporal. So in a picture, you see, if you just want to send every pixel, that's just huge amount of data. Like you need terabits per second link for this 8K video, raw video, every pixel. But as you can see, these are all blue, right? All blue. So you can just say blue, and you can say the next 1,000 pixels will be blue. Right? So that's a compression, spatial, within the frame compression. There is a frame 1 and there is a frame 2. You can see it's almost the same. Something has moved. This guy is jogging. Moved a little bit. So it's a temporal. In time, you can compress. You can say in frame 1, it goes like this. In frame 2, only change this thing. That's the temporal compression. So all these compressions, so all the videos that you watch via Netflix, via Amazon, they are compressed using the standards called MPEG. Right? So MPEG is very popular. The problem is, like, as you can see, if you use MPEG 1, then it's 1.5 megabits per second, so there's lots of loss, right? So if you use 6, then it's a higher coding. So you can see when you compress, you have to make a decision. How do I compress, right? So if you compress too much, then the quality is reduced, right? It's very good for your communication. So if you have getting only 4 megabits per second connection with a mobile device, then you are happy because it is coming on time. Because video means it has to come on time. Every single frame that you want to display has to come within sort of strict time delay because we are watching 25 frames per second. And if you do not maintain that time, then the video is not good. There will be jerkiness, there will be stopping, and all sorts of user experience problem, right? It's not like a file, I wait for 2 minutes, the file is downloaded and I'm happy. It's not like that. So video is very time sensitive. So if you do not have a lot of bandwidth, you like this strong coding, which reduces significantly. You don't care too much about the quality at the time. But if you have a huge bandwidth, sometimes the bandwidth is very good, then you wish that the coding was not that strict. Like, I have bandwidth, why shouldn't I watch it at a higher quality, for some higher resolution or a higher pixel values? So you see the problem in the internet is the bandwidth that you are getting is not fixed. Right? It's not a circuit, it's a packet switching network. So it changes all the time. So when you're downloading, if you're watching, what's the throughput you're getting, you'll see it's fluctuating all the time. It's not a fixed thing. Sometimes 20 megabits per second, sometimes 5 megabits per second. So if you're watching video, then you need a standard that can take care of that and gives you the best encoding at the time. How do you do that? So what they do in the internet, like Netflix, they take a movie and they chop it up into small chunks, 2-second or 10-second chunks. Every 2 seconds, they encode it into multiple bit rates, high quality, good quality, medium quality, every 2 seconds, very different. And they are just using HTTP. Just store it in an HTTP server, and they are giving us URLs in the manifest file. So manifest file is the main file of the movie, which says that this is how you need to get, this is the URL to get this encoding for the first jump. If you want the higher quality of the same jump, then go to this URL and things like that. Right? So you have all the information in the file. So this is the new standard that we are using at the moment. So this is called Dash. The main thing is dynamic, is adaptive, right? So this is called Dash. So all the intelligence is in the file. Once it downloads the main file, manifest file, it has the intelligence. So you can use its own intelligence to decide, monitors the network bandwidth, and it fetches the right quality for the next 2 seconds. And that's why you get a very high quality watching, irrespective of the fluctuations in the internet. The result is the video is actually stored in so many different servers, and you might have to fetch from so many different servers. And then they have this the load balancing, because if a lot of people are downloading from the same server, then the server bottleneck happens. So they have to distribute the jumps to many different servers, right? So who is going to manage all these things? So if I am Netflix, I want to focus on contents, right? I want to get the right movies. I want to do the encoding of the videos, right? I don't want to get into how to store the HTTP servers in the world so that the users get all these things. So different industries were developed in the last 10 years. So some focusing on the content, some focusing on the payment system, some focusing on the storage, right? Where the work chunks. And then how to use DNS successfully so the users always fetches from the geographically closest one, right? So this is the link between CDN, Content Distribution Network, and DNS. So DNS plays a huge role underneath the Content Distribution Network. So the content is always coming from a local closest point and easily distributed. So I will go straight into this picture to show you this. Then you can read the other slides. Okay. So this is a generic one, and then I'll show you a case study. So the generic one is here, NetCinema, for example, right? And you are a client, Bob is a client, so it has to open an account, right, in NetCinema if you want to watch a movie. And then they say, yeah, there's a good movie, you can watch it with only $4 if you watch it this week. So you click on this URL, say I want to watch this movie. You click on this URL, but this is HTTP, so it is the IP address of the server where this file is, right? So it is DNS. Step 2, Bob's HTTP client sends a request to the local DNS. This is Bob's local DNS server, step 2. And in step 3, it sends to the authoritative DNS server of NetCinema to find out the DNS, the authoritative DNS. And then this NetCinema is saying, oh, authoritative DNS for me is here, because King is another company.
What? Just ended. Anyways, I'm going to go back to this. Can send file, can receive file. Can I put them into one? Not sure. How does Cecilia know my freaking YouTube channel? Oh, no, she would. Okay, can't connect, get files, check file not found. We'll do the bandwidth later. This entity can receive. No, we'll throw the ID. Cause yeah, no, that's from ID. To ID, fine. If density dot can store. Then we throw new. Actually, so we can do it. We can add a can store file in entity. Should I do it like that? Because devices can store an unlimited amount, right? by just a string representation of their content and a file representing their name. Yeah, no. I feel like maybe we'll have something like that instead. What is it? Do I need to override it? Remember, it's not a race. Everyone's got these days. Oh. So satellites have bandwidth. Okay. Well, relay satellites. Yeah, no, whatever. Okay. Install file. Okay, so we're in a standard satellite. If max files equals 3. Can I do size? Is equal to max files or files dot content dot values. Can I do a reduce method? So this is subtotal element. Should it be override? Yeah, no, okay. Let's change friggin' entities to Should we have a string? Should we have like a file? What does a file need? It needs a title, it needs content, it needs content length. Yeah, okay. Let's make a file class. We don't really need getters and setters. We don't really need to set anything. All we need to do is set this one. So we will return a file? Or should the blackout controller not know about it? No. I feel like that makes sense. And then blackout controller. Info response. .getFiles. Files.put. How does put all work for friggin'? Who? It's the exact same. Whatever. So string data will be file.get content, and this will be file.get length. Is file complete? What do you mean string cannot result to a variable? You're an absolute dummy. It says file. It's not. It's not a file. I guess I can map it to like. I guess we'll just make this void. What's the status satellite done? So it can store up to 200 bytes. Ah, okay. Boolean max bytes. It'll be static, right? What? Oh, why does it say Boolean? I'm such a troll. That means it should be. It's less than or equal to max bytes. And then return true. what? Relay satellites still have a list of files, I'm pretty sure. So I can't send it too far away. I don't know. Whatever, doesn't matter. Method is not applicable. It should be file size, Aaron. Otherwise it returns null. virtual file, no space, stored exception. That's a bit more complicated with the bandwidth and everything. Files and min transfer. This includes the full size of.
It's a lot more complicated than I initially expected. So it'll be the file and the bandwidth. Huh? Get the bandwidth. Huh? How do I do this? We can tell them I'm going to send you 20 bytes. For each simulate. So you can download the file. Card. Title, bandwidth. like that. And for each download. So it'll be the current byte. And got these days. So you can try to send everything. And phew. Do we just need to simulate it? Like, can we actually just send the whole file each time? It's a lot easier that way. Bandwidth content. So we'll know the file size before we finish. How do you... Is it not string dot substring? Something like that. Because if the bandwidth is 3, if the bandwidth is 1, and on the next simulate, you can read 1 byte. Right. So you send the whole thing quickly. Content will just be an empty string, and length would be and false. Hmm. What the fuck? What is this? Bro, my brain is not able to wrap my head around this trash. Whatever, doesn't matter. Okay. So it downloads a new file in the first minute instantly. And then in the second minute.
Void move. So all satellites need a download. So if I can have a title, content length. Let's check the comp 2511 form. Honestly, because your boy is very lost. What the frick? I should just try, honestly, but like, oh my goodness. What the frick? No. I don't want to do friggin' depth first search in Java. It'll just be add file to device, right? Device.get SID. Send file. Alright, frigate. So it's not a boolean. Bandwidth exception. Okay. So when you download a file, transferable bytes are 1. Bytes to transfer are T. Bytes. The next bytes depends on the bandwidth though, right? Am I tripping? If you have a bandwidth of 8 bytes per minute and are currently downloading 8 files, you cannot download them. Oh, okay. Can send 10 bytes per minute. Can receive 15 bytes per minute. Send file per minute. Can receive 15 bytes per minute. Can send 10 bytes per minute. Has bandwidth to send. Sending bandwidth. Yeah, no, it would be the same logic, right? Receiving is 10. I still need to do communicable.
Sending. If you're sending from a satellite to another, currently has 2.
like it's better to do, like it's less efficient, but it makes more sense. We should have like a public. So return sending bandwidth. So if we have two devices, we just want to divide it by a number of devices. I did not know how to spell receiving. Whatever. So it'll just be sending divided by num files. Sending. However, if it is, and it has to be a hot number. One equals 10, 10 divided by 2 equals 10. 10 divided by 3 equals 3. 10 divided by 4 equals 2. 2. It has to do something with modulo. Whatever. 10 divided by 6 equals 1. Okay, so what is the deal here? Ten mod 2. What is 10 mod 3? No. Oh, actually 10. That looks right. Floor division. Less than or equal to the normal division result. That's technically correct, but about 15 divided. Yeah, 15. 15. Divided by 4. I'm gonna just ask ChatGPT. Honestly, it's a ChatGPT kind of question. Divides something. Use the floor. What, like, who's Dan? Does Dan know what I'm trying to do? Cause I don't know. Cause I'm using the floor function here in friggin' Python, and it looks like it's giving me the right output, but I can't mathematically prove that the floor function will always give me the right output, which is what I'm worried about. But if Dan says the floor function will friggin' work, I might use it. I want the result to also be a whole number. Something like this. Dan is Daniel Koo. Oh, yeah, that. Oh, this is Daniel? What the frick? Yeah, I know Daniel's correct at math. So you were able to deduce that 10 divided by 3 will somehow go to, will become 9 divided by 3 because 10 divided 3 doesn't equal 0. Something along those lines. It will. Like, I can just do it. So the floor works like that. Like, I saw it working in Python and I was like, what? No way. Can I put 2 slashes for the floor? Nope. Wrong language. Sending bandwidth 5%. Sure. Yeah, I could just do something like this though, if I was really scared. Could it be argued? You're telling me that these 2 pieces of code are the exact same? I feel so safe with this one though. Whatever. Actually, what's 10 divided by 11? Okay, and 0. That's good. So I can just do something like this. Devices can send an unlimited amount. Alright. Can you do int dot infinity? Math.int max or something. Oh. Fair enough, fair enough. Thank you. What am I looking for? It's 10.7. What is 1 divided by 1? Math.int max or something. Yeah, no. Integer.max value. Oh, that's a thing? That's interesting. Whatever. Sending bandwidth. I feel like this makes the most sense. It's like with another file. I feel like that makes more sense, honestly. Do I need the override? I don't know. Could get an array of file. So you need the file, and you need the Brr. I don't want to do this no more.
So instead of num files being sent, we can just say private it should just be an array. Right. File cannot be resolved to a type. So files can have a source and a destination. Cannot convert from null to int. I know, it probably is more than
Actually, yeah, well, we shouldn't be changing the source and destination mid thing. We should just use polymorphism. That's what I want to do. How to null and source ID. And they both will be the source ID. Yo, Daniel, how are you friggin' implementing file transfers? I wanna cry. Let's add file. Did they give us add file or add file to device? Device dot. Oh. You can chuck in a device ID as well. Why not? Device ID. I finished it a few hours ago. What's good? What? Oh, mate. I need you to help me out. What the frick? Oh, device IDs are strings. I'm tripping. Oops. Oh, okay, no. Strings are nullable though. Okay. Whatever. And the source will be No, I don't want to do this. I'm so dumb. I don't know how to do it. Let's take a break. Hee 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 hee. Why do I have a notification? Okay. Back to move. And then queen takes. So I can't do that. How about rook takes? King. And then once king is there, then I can do this. And then the king can go here. What the frick? Why is Patrick Aussie wanting me? Oh no. Oh no, I'm gonna lose this, aren't I? and you're still taught on slopes. Yeah, nah, bro. I can't be bothered. I literally can't be bothered. Whatever. This is a good break. I ain't gonna lie. Sure. Oh, that's why I did that. Okay, fair enough. Get on Santu, mate. Let us see. Interesting. What should I do? Whatever. Just do some VM, pretend that we're winning when we're not winning. Oh my goodness. He'll probably just bring this down as well. That's not the best for me, I ain't gonna lie. I don't know, mate. I don't know. What's Patrick gonna do? Sure, I'll take it, I guess. Is he gonna check me or something? Oh. Anyway, oh, I can't take that. Am I tripping? Oh, whoops. Did not mean to do that. Whoops. That was a pretty bozo move. I ain't gonna lie. Anyways, let's pretend that didn't happen. Threatens this and threatens the knight as well. What did he take? I forgot. I didn't see what he took. Whatever. Oh, I did not see that. Not bad. What's the haps? Apparently we're even. I feel like I'm losing though. just do a cheeky check here. If he goes there, I guess I'll bring my queen here. That should be mate. If he goes there, then I can bring my rook, and then he'll be forced to come over here. I feel like it's mate either way. Oh, actually not bad. Okay, it's not mate because I didn't realize you could block like that. Oh, frick. What can I do? What can I do? I'm close to mating, but I'm not there yet. His horse is pinned, which is nice for me, I reckon. Where do I want to bring my horse? Oh, since his horse is pinned, I can take this. I forgot about that. Yeah, nah. That's fair. Where's he gonna go? And if he moves his king there, then I can get a fork. Okay, no, he didn't. That would have been cool though. Let's see. Where to move next? Where to move next? I could go here. I could go here. Well, I could go here as well, which is pretty interesting. Since it's an interesting check, I'll do it. Is he gonna trade? I don't mind trading, I think. Okay. Oh, it's not check. It's not. I'm not getting any more checks. That's not good for me. Okay. How about I? So if he does that, then I can do that. No, I'm just losing if I do that. Oh, but I can pin the queen to the king, which is nice. Oh, frick. Nah, it's the king is still pinned, which is nice. What's he gonna do? Maybe something like that. Oh, frick. He did exactly what I didn't want him to do. Oh no. Oh, frick. Oh no. I didn't. Okay, nah. I need to go back to coding. Frick. Oh my goodness. Too good. would be cool if the blackout controller were to. Let me ask Daniel. I wrote them in the entities. I wrote code to pull all the files in progress. And that makes the most sense. But if you put it in the blackout controller, it could be a bit easier. I ain't gonna lie to you. My entity file is so fat. The entity file is the fat one. Same as blackout. Entity file. Yeah, 140 lines, wow. Sheesh, what the frick? Process file transfers, something like that. Download files in progress. You can't just do that, can you? Transfer files. Do relay satellites have any? They don't.
So really satellites aren't really satellites.
So for each entity, I guess they can have a num files being sent. Now forget, I am going